Right now, a spacecraft is flying through the outer atmosphere of our Sun at 430,000 miles per hour. It is flying directly into the origin point of the solar wind. The solar wind is a continuous stream of electrically charged subatomic particles that rage across the 93 million miles of space between the Sun and Earth. When those charged particles reach us, they interact with our atmosphere to create the aurora borealis. But this stream of particles poses a severe physical threat to modern infrastructure. A strong enough solar storm can induce electric currents capable of overwhelming our power grids and disrupting global communications. To protect our technology from this distant threat, we have to study these solar storms at their exact source. In 1958, astrophysicist Eugene Parker first theorized the existence of this solar wind. But his theory introduced a massive physical mystery. How do these particles manage to accelerate fast enough to escape the Sun's immense gravitational pull? For decades, we couldn't answer that question. From Earth, the solar wind arrives as a mostly steady breeze, and distant space probes couldn't detect the chaotic forces at work near the stellar surface. To gather the missing data, NASA built the Parker Solar Probe, a specialized tool designed to physically touch the star. The probe recently completed its 26th and 27th close approaches, diving to within 3.8 million miles of the solar surface. By crossing the vacuum of space to graze the Sun, the probe is capturing direct observational evidence of mechanics we previously could only simulate. As the probe crosses into the corona, the Sun's outer atmosphere, the steady breeze we feel on Earth disappears, replaced by violently shifting weather. The probe uses an instrument called WHISPER to capture high-resolution images of coronal mass ejections. These are massive, sudden outbursts of charged particles that drive severe space weather. Up close, massive ejections physically pile up, colliding with one another and tangling their magnetic fields in real time. The data also revealed switchbacks. These are zigzagging, localized reversals in the direction of the Sun's magnetic field. These magnetic funnels provide the burst of energy needed to power the fast solar wind, which travels out into the solar system at speeds exceeding 1 million miles an hour. Extreme proximity to the Sun was the only way to observe these chaotic magnetic zigzags and finally link them to the fast solar wind's acceleration. We are watching the exact mechanisms that birth space weather unfold right in front of us. If you want to keep exploring the physical systems governing our universe, make sure to subscribe. The fast wind is only half the story. The probe must also untangle the slow wind, which travels at half the speed but is twice as dense, making its behavior highly complex. This split screen illustrates two distinct origins of the slow wind. On the left, Alfvenic wind containing small-scale switchbacks escapes from dark, cool coronal holes. On the right, non-Alfvenic wind, lacking magnetic variations, originates near helmet streamers, large closed magnetic loops where trapped particles break free. Flying directly through these streams allows scientists to measure their unique properties, proving different types of space weather are driven by completely distinct atmospheric mechanisms. All of these individual mechanisms are currently amplifying. The Sun has officially entered solar maximum, the peak of its 11-year activity cycle. During solar maximum, the surface churns with frequent, violent eruptions, throwing intense, highly unpredictable space weather out into the inner solar system. Because the Parker Solar Probe has been orbiting since 2018, its 27 close encounters have effectively sampled the solar atmosphere as it evolved from a quiet lull to this explosive peak. Scientists are now taking this high-resolution forensic data and feeding it directly into Earth's space weather models. By capturing the physics of these storms at their exact origin point, the Parker Solar Probe is turning chaotic threats into actionable forecasts, giving us the lead time required to protect our infrastructure from the next major solar event.